The reason we want to do that is because AI as a single workload has been growing extremely large. So starting from maybe 2023 with ChatGPT and all the Gen AI boom, before AI has been at one small workload potentially in the data center, but now it takes entire data centers to just do AI. Very recently, they've been using multiple data centers to train one LLM. So it has been attaining unprecedented scale. Media coverage is typically about how large it could potentially be, and also the implications of it being so large. Especially here in the US, I think it has been raised to the level of national security because AI itself has become such a important skill and technology that is so future looking that the countries cannot afford to lose in the AI arms race. As energy and power started to become the bottleneck of doing more AI, finding power energy started becoming a national security issue and a national economic growth issue. With a lot of demand for energy, there's two ways to go. We should probably do both, is to increase our energy supply while being mindful of whether it is sustainable or not, and also try to decrease the amount that we spend. The former is a little bit harder for computer scientists like me to do, but the latter of identifying demand of energy and trying to optimize it is what we call ourselves the ML.ENERGY Initiative tries to take as our mission. It's just a group of computer science people that initially me and my advisor began at the University of Michigan, but now we do have a couple other academic partners working with us, Washington, MIT. We want to do three things in terms of energy. We first want to very precisely measure, and based on that measurement, ultimately understand what energy is as a systems resource and how it relates to other existing important metrics, especially ML, like time or model accuracy or user responsiveness. We find it very important that those understandings and measurements eventually flow into optimizing what we typically call energy bloat. So we all know about software bloat, where it kind of says the code base grows and grows, features increase without really noticeably improving end user experience of that software. Energy bloat is the same thing. So the thing keeps increasing in terms of its energy consumption, but is it really providing noticeable gain in terms of a certain metric, like making it faster or increasing the accuracy of the model? So if it starts giving diminishing returns or potentially no return, we start calling that extra segment of energy bloat. And how do we trade off that automatically? And how do we expose that trade-off to users so that users can, just click or select them up and the rest will be done automatically. So that is the general computer science stuff that we want to do at the ML.ENERGY Initiative. That is the order of things that I will introduce today, and I will begin with measurement and understanding. So it's about when we do ML stuff, where do the joules go? And we kind of know where power goes. Energy is power integrated over time, and typically the way data centers provision power, so this is from an AskPlus paper, which is from Microsoft Azure. So they actually do the data center, and I think this is one of the more representative data out there, is pretty much half of it is GPUs, and then 1/4 is on like fans, cooling. And then CPU takes like a little slice, and all of the others added together is, less than even cooling. Others would be storage, memory, and the networking fabric, the switches. So GPU, especially in terms of ML, is becoming a really important power consumer. So the building block of all of our measurement and understanding and optimization is the software framework we're building. We are calling it Zeus. It has two components, measurement and optimization. I'll start with the measurement component. We aim to provide a Pythonic API that lets people programmatically measure the energy consumption of their deep learning application. So with this, what we've done is it's been, I think, about 2 years ago, when LLMs first began, we literally took like tens of popular models and just measured their energy consumption, all of it. So that was V1. And now we're currently at V2, where we not only we have LLMs, but inside LLMs, we have chat, code gen, and multimodal LLMs like VLMs, and also image and video generation with diffusion models. So I want to briefly touch upon the insights that we obtain through this measurement. So if we look at it, it's three types of models. Left is LLM, middle is multimodal, and right is diffusion model. And the y-axis here is average power consumption over max power. So the A100 GPU's TDP is 400 watts for our case. So if average power over max power is 50%, the thing is consuming 200 watts. And the general trend actually also holds for energy. So this is a pretty representative plot. And the full plot is already in the publication down below. One of the things that we can kind of learn here is that LLMs generally consume less power than diffusion models. So that is because LLM inference, especially LLM decoding, is very memory bound, and it doesn't fully utilize the GPUs at SEMS compared to diffusion models, which are completely compute bound. And in the middle, there are the multimodal models where their prefill, which has to run the vision encoder, is much more compute intense, and therefore it also consumes more power. So now we start changing the parameters. What if we use an H100 GPU? So from an A100 to an H100, what kind of changes is diffusion models keep consuming nearly maximum power because even on H100, they are very compute bound and they will still nearly fully utilize the GPUs as SEMs. Whereas for LLMs, they are still memory bound and it is still bound by the GPU's HBM bandwidth when memory latency. TDP is short for thermal design power. It is like the hardware vendors promise to you that the hardware will never draw more than that. It may momentarily slightly draw more than that, but on average, it will not draw more than the TDP. Historically, it's called thermal design power because it's supposed to mean that it will not thermally melt the GPU. So if you draw more power than that, they're like supposed to melt. So that we can pretty much take that as a maximum power draw of the GPU over a reasonably long time horizon. That try to optimize operational carbon does a lot more of those kind of temporal and spatial shifting because energy is kind of the same wherever you consume it, but carbon is a bit different, right? Because the time you consume and where you consume affects your carbon intensity. And that's why you would move around workloads spatially or temporally. So for energy, we might be moving due to power availability. Another problem, though, that I would mention that it's very important there is everyone would want to run their thing in either where energy is cheapest or carbon intensity is lowest. So it is not a sort of panacea. We have to do a lot of scheduling, and whenever everyone wants to move to the currently best location, there will be contention in that place. So I feel like there has to be some very good scheduling and prioritization when one has to apply that kind of shifting solutions. So yeah, this slide, next slide, it's showing that hardware choice matters. So also what matters is algorithmic choice. So one of the things that we found here is, so we're comparing Phi 3 mini and Phi 3 small. Those are models of different sizes in the same model family. But it happens that the smaller mini model, which is like 4 billion parameters, whereas the small model is large, 7 billion. But the smaller model uses multi-head attention, whereas the larger model uses group query attention. And group query attention basically uses less memory per token. The implication of that at the serving system level is that when you use a more memory efficient architectural choice, you can increase your batch size. And when you increase batch size, you can amortize energy and power over more workloads better. So your per token generation energy consumption or power draw is reduced. What we see something very interesting here, because even if the smaller mini model is smaller, it'll consume slightly more power. It shows a very interesting thing where algorithmic choices at the model level has direct impact on energy and power. Finally, another knob that matters generally is deployment choices. So we have a couple other examples in the paper as well, but if you see Stable Diffusion X Large, there's the original SDXL and SDXL Turbo, which has been tuned for lower image resolution. And it's kind of obvious, but when you produce lower resolution images, then the latent size decreases, the amount of flop decreases, and also the amount of power and energy. So and this one has implications for user experience. So what I see here is a very complex trade-off between a application optimization end goal perspective versus the cost of you providing inference to that application. Developers might want to survey or figure out the end metric user experience goal of that application and then propagate that information back into the backend where stuff like image resolution or for diffusion models, the number of diffusion steps, all of those has to be tuned. Right. So for this specific one, for the purpose of benchmarking the ML side performance, we're kind of deferring to community benchmarks, like because there are so many benchmarks for the ML side. There's like Rethink benchmarks, there's Math, and there's Arena user alignment. So for the ML part, we're deferring to other leaderboards and benchmarks. Here, we are just showing energy consumption and power when we change the model, change the task, change deployment, and everything. We do have all of it open source, and we also have knobs that let you choose some level of application level performance. So if you take a look at our leaderboard and there's like a checkbox saying show advanced like columns, you can change, for example, the average time between token or time per output token or time between token. There's no consensus on terminology, but for LLMs, you can tune that from like very fast token generation latency to slower ones that are more closer to human reading speed. And you can see how energy changes based on those performance goals. So, and this is one of the things that I think is very important. And I will reiterate on user experience in application building, because when, for example, you're building a TTS system that is getting text from an LLM, as long as I speak in English speaking typical speed, then like everything is fine. So there's really no need for the serving system to generate as fast as possible. That performance goal in the application level can propagate back to the LLM inference side and reduce energy. So I feel like all of these measurements are very valuable in making these optimization decisions. And I will move on now to how are we going to use these measurements for actual optimization? So I have two quick academic works to cover. The first one I will talk about is for training a single large model. So when I say a large model, I mean basically an LLM or a multimodal LLM. And these days, training just one of them, even these numbers it's like 2023. Unfortunately, I don't see any newer numbers, estimates up there yet, but just training one of them can be compared to like a lot of code. So optimizing a couple of these large model training runs have already very big implications. Large model is very large, and you typically cannot even fit the parameters into a single GPU. So you have to slice the model in this dimension, that dimension, and other dimensions into small pieces, and then spray it on multiple GPUs. So depending on the dimensions you slice, you can call it data parallelism, tensor parallelism, pipeline parallelism, and like expert parallelism. There are many degrees of parallelisms you can apply to a single large model in order to distribute work to multiple GPUs. One of the dimensions that we find to have implications for energy optimization is pipeline parallelism. What you see here is the large model, and we sliced it into 4 pipelines. So there's like multiple layers, and we sliced them in the middle into 4 contiguous pieces. And we call them stage 1, stage 2, stage 3, stage 4. So, for example, a forward pass will start from the first stage, traverse stage 2, 3, 4, and then the backward pass, the gradient one, will have to go backwards. So it'll start from 4, 3, 2, 1. And then we will interleave multiple of those forwards and backwards into like one big complex graph to execute it more efficiently. So given this, on top of this, what we kind of observed is when you slice and dice the model into hundreds of pieces, you can rarely split that into perfectly equal sizes. There are some variation in the slices of computation that some GPUs have and other GPUs. This is what I've drawn to scale. This is training GPT-3 1.3 billion on 4 A100 GPUs. And we tried to do the optimal slicing. And even then, you can see that some of the boxes are smaller than other boxes. So it ends up that other than the operation on the critical path, other ones don't really have implications to the end-to-end training iteration time. Which means, for example, operations like F5 here, the fifth forward, it can slow down a bit, and it's not going to affect the end-to-end iteration time. So when we color all these computation boxes with actual power consumption, we can figure out mathematically how to precisely slow down every single one of the non-critical computations in large model training, which doesn't change the length of the critical path, gives us free power and energy reductions. So this is the gist of the paper Perseus. We've shown it for like 5, 6 different large models that we can automatically figure out this slowdown plan, and we can get up to 30% energy reduction without any training time slowdown. We proved in the paper that the thing is NP-hard. So yeah, we don't really have a closed form solution, but in the paper, we show that the final solution and the actual upper limit solution, which is unattainable, is pretty close. So empirically, we're kind of okay. And to answer the first part, is it a heuristic? Our algorithm is pretty interesting. We figured out that finding these precise amounts of slowdown is equivalent to solving a max flow problem, max flow min cut problem. So we iteratively solve that to slowly compress this into like the close to optimal form.
Okay.
So in our evaluation, the longest thing it takes is like 20 minutes. But to be real honest with you, with more stages, it'll take more. So we have 4 stages and 8 stages in our eval. If you start increasing stages even more, it can take like hours. But we kind of get around that by saying large model training takes 3 months and you can like spend the day optimizing it is probably fine.
Sure. Thanks.
And do you know if these kind of approaches are also used in practice already? And if so, by what kind of companies?
So we are talking to Meta, which I am currently in. The first technical roadblock actually is the way we slow down this computation is by reducing the GPU's frequency, which gives us like, we can precisely control execution time and get energy reduction. The problem is, in order to change the GPU's frequency, we need pseudo, basically. And that typically doesn't happen in big tech companies. So we have to figure out a way to either get approval for this particular application or, I don't know. It's a NVIDIA driver level enforcement, so it's very difficult to get around that. But technically speaking, I don't think there's really a technical roadblock other than that.
Okay, thanks.
All right, so now I'll move on to the final thing, so this large model, this Perseus thing is reducing energy for one job. It doesn't change time, it reduces energy. But I implied earlier too, can we reduce even more energy? It'll probably slow down a little bit, but what is the trade-off? How do we characterize the trade-off? And once we see that trade-off, and how do we find the optimal parallel frontier? How do we navigate to that? And how do we give the users the choice? Because typically, when you train models, you sometimes want it to end as soon as possible. You hit train and then go home. And as long as it's done by tomorrow morning, you're fine. So we do want to empower users to make that choice. So the third part is how to navigate the performance energy trade-off. And we just trained pretty much every combination of batch size with different GPU power limits. So a GPU power limit is a GPU hardware level knob where if you set the power limit to 300 watts, for example, it'll never consume more than 300. But it will also slow down your application to some limit, so to some amount. So it has implications for computation throughput and power, and therefore also energy. On the other hand, batch size, it changes the amount of compute you do over time. So it also has implications for time, power, energy, and also the model's final accuracy. So that is the problem. And when we collected all these data, we made sure we train all of the models up to a fixed validation accuracy so that all of these gray dots are not degrading model quality. So once we trained all of it, we could see a pretty clear parallel frontier existing. It is a very nice one, a convex one, where at this point, we are only sacrificing a little bit of time. But in other words, at this regime, when you reduce time, you are only getting diminishing returns out of the energy you put in. So the users now get to ask the question, which yellow point is the best? And they get to choose a line, and then our algorithm will automatically find the combinations of knobs that have them land directly on the parallel frontier by changing batch size and GPU power limit. And these are for not large models, for single GPU, smaller model training. But in theory, there's no reason we cannot apply it to large models as well. And all of these, for example, just the power limit optimizer part, there's also the batch size optimizer, the Perseus optimizer. They're all part of the Zeus library. That's the second part, the optimization part of the library. So particularly for the power limit optimizer, we try to make it as easy as possible for people to use. So we also have a Hugging Face trainer callback adapter where you can just instantiate the thing with our monitor, and then you can plug it into the Hugging Face trainer, and it'll just work. So this is my final slide. It's acknowledgement. We have the ML.ENERGY Initiative people, and inside there's the Zeus team and a bunch of professors, including Mosherov, my advisor. We are completely open source. We are research-based. We're also trying to get more adoption in the industry as well. And we are always happy to chat, always happy to collaborate. So let's talk anytime too. Thank you.